right, today we're going to keep looking at derivatives. We're going to look at another type of differentiation called implicit differentiation. So far we've learned how to find derivatives, and that derivatives find the slope of a function. How would we find the slope of the tangent line to this circle over here at the point 3, 4? So some things to notice about this circle: they do give us the function here. Notice that because there's no numbers being added or subtracted from x and y here, the center's at 0, 0. Also, from equations of circles, that's the radius squared. So we know over here that our radius is 5. So that would be 5. That's negative 5. This would be positive 5. This would be negative 5 down here. So the 0.34 would be somewhere maybe approximately right here is the 0.34, where this is at 4, that's at 3. If we were to draw the tangent line, remember tangent line's that line that's the same slope that skims the curve, it would look something like that. So how do we find that out? Well, what we would need to do then is find what is the derivative of this circle equation. But if we try doing that, usually when we do derivatives, we have this y equals equation. This we can't necessarily solve this for x, because if we try doing that by subtracting x squared, then we get that y squared is equal to 25 minus x squared. We can square root, but then if we square root, we get that this is plus or minus the square root of this. And that becomes two functions, and we don't want to have to deal with trying to do two functions. And so solving it doesn't really work, and the reason it doesn't work to solve for y is a circle is not a function. It doesn't pass our vertical line test. So what do we do then to find its derivative? Well, we're going to use a process called implicit differentiation. And how to do that is we want to differentiate, meaning find the derivative of both sides of the equation with respect to x. So what that means is each time you differentiate a y, then you got to make sure you include the derivative, which we're going to use dy dx. Next, we're going to try to collect all those derivative terms on one side. If we need to, factor out the derivative and then solve for what that derivative is going to be. All right, so let's go back to our problem that we've been doing. Let's see if we can use this implicit differentiation. So you want to take the derivative of everything first. So derivative of x squared would be 2x. The derivative of 2y similarly would be 2y, or x squared would be 2y, but we have to include, because this is y, we have to include the derivative dy dx. Equals, and now derivative 25, that's a constant, that derivative is 0. So next, now we want to solve for that dy dx, which is our derivative. So we can do that by subtracting 2x. Next, we can divide by 2y. And so now we got our derivative here, which is dy dx. And that would be equal to the division of these two things. While we're at it, I'm also, since both of these have a 2, I'm going to cancel those out. So our derivative becomes negative x over y. Meaning that, and you could also write as y prime, that our derivative is always going to be whatever the x value is over the y value, and then if you take the opposite of that, that becomes the slope. So let's see if that works. Let's see if that works here for our problem here. So what we want to find is what is the slope of that tangent line at the point 3, 4. We got our derivative. We just found that dy dx, or if you want to call it y prime, is equal to negative x over y. So now if we want to evaluate this derivative at the point 3, 4, that's what this notation means, plug in 3 for x and 4 for y, and there is no simplifying. It would just be negative 3/4. So if we come back to the picture here, we estimated that that point was right about there, the point 3, 4. There's that tangent line again. So the slope of this line right here, according to what we did, that slope is going to be negative 3/4. And it definitely looks like that is going about down 3/4. So that would be the slope of that line. Now, you might get asked follow-up questions such as this. Find the equation of the tangent line then at that same point. And then it says also sketch it on the circle. So if you already know that our slope here, our dy dx, our slope at 3, 4 comes out to be negative 3/4. That's our slope here. We have our point right here. That's our x and y value for our point. Now use like point slope form and you can get the equation. So if we plug everything in, we get y minus 4 equals our slope here. So that would be the equation. If they ask you to get it in slope-intercept form, you definitely could by distributing here. Let's just do that so we can see graphically if it kind of makes sense. So if I distribute that negative 3/4, that would be positive because we're multiplying two negatives. 9/4. And then we got to add 3 over to the other side. I'm going to add that 3 over as 12/4, which is the equivalent thing to 3 with the same denominator there. So then we get y equals negative 3/4 x. 9 plus 12 is going to be 21/4, which is a little bit over 5. So if we sketch this out now, let's see if it makes sense. We're going to sketch that tangent line again. We estimated 3/4 to be about there. Our tangent line's that line that skims that, and the equation of that was y equals negative 3/4 x plus 21/4, and 21/4 is like 5 1/4. Remember this point, because the radius was 5, is 5. So that does look like it should hit the graph just over 5 there, and it does have a negative slope, and yeah, that would be the equation there. So that's the process of doing implicit differentiation.